pass it around. This is crystal bar titanium, if I remember. Yeah. Okay. I don't have a piece of crystal bar zirconium, but this is, you showed crystal bar zirconium, a picture of it. They're both made the same way. You start with zirconium oxide or titanium dioxide, which are both relatively abundant in the Earth's crust. But then you have to convert them to zirconium tetrachloride or titanium tetrachloride. And titanium tetrachloride, we make probably several million tons a year, because we then take that titanium tetrachloride and we oxidize it to very finely divided titanium dioxide. And all the paint in all these rooms is titanium dioxide because it has a very high specular reflection. Actually, zirconium oxide has a higher specular reflection than diamond, which means it refracts the light better than diamond. Okay, and so if your fiance doesn't like cubic zirconia, it's because she doesn't want something that sparkles more than diamond. Other than that,
That'll work.
One of those extracts.
So that's crystal bar titanium. That's the raw product. They basically start with hot wire inside a vacuum system, introduce the titanium tetrachloride. The chloride goes off, decomposes, and it leaves behind a crystal of very, very pure titanium. This is actually a piece of zirconium tubing, just like you said, centimeter diameter fuel pellets go in there. About $30 a foot, or $100 a meter, 100,000 meters, as you said, in a typical reactor, so that's $10 million for that stuff, just to clad and hold the fuel. Okay. Navy reactors are smaller, but you're still using zircaloy, because I think the 0.81 Barnes is the lowest of anything on the periodic table. I once saw a periodic table that had the Barnes for every element, and I think zirconium was the lowest. And boron is, not typical metals are around 3, or you had iron and some nickel, and they were 3 to 5 rather than 0.18.
Yeah.
I think boron's like 20 or something. Okay, that's why you use borated water to control the neutron flux. Boron has a very high Barn cross section. Don't ask me what a Barn cross section is. Okay. We talked a little bit about hipping yesterday at the end. And this is something I had the file. This is actually on titanium alloys. I had in the notebook. And it shows the fatigue strength of wrought, which basically means forged titanium, which is pretty pricey. Cast plus high static pressure or cast. Now they overlap quite a bit, but nonetheless, the hot isostatic pressing can get rid of any voids that are in the material and squeeze them out without changing the shape of the product. So you can think of it as forging without shape change. Actually, this was an interesting repair on the back. The Air Force put in a $10 million system out in Oklahoma City, is where they repair all their Air Force does their own repair of their jet engines. And this is a turbine blade. The tips are worn off, and they built up by welding 25 weld passes. That's 1 millimeter, so they built up about less than a centimeter, probably 7/10 of a centimeter or so. And they're going to machine that, okay? But they're refurbishing this blade, and they're showing the different microstructures you get and stuff. But there's like 25 weld passes, one on this side, then one on this side, then one on lots of little bitty weld passes to build that back up. Why? Because this type of vein, it's not hollow, it's not single crystal, but it still probably costs $500 or $1,000, and it's worth repairing it if you can, as far as that goes. So, any questions on any of that? It's just kind of a catch up on some things. Here is something that basically shows you. I'm going to talk about lightweight materials. This came out of a book on lightweight materials, understanding the basics. Okay. And so we've got steel, titanium, aluminum, magnesium alloys. Steel can have tremendous strength. Okay, this is megapascals, so we're talking 250 KSI. These are the types of things like 300 M. Before we went to titanium landing gears for aircraft, we went to, we used to have 250 or 300 KSI steels, which are very susceptible to hydrogen embrittlement. Tremendous amount of maintenance to make sure you don't have any hydrogen embrittlement or corrosion on those things. The interesting thing, I remember, I was told the first thing you design, if you're going to build a new aircraft, is the landing gear. Because everything else depends on the landing, the weight of the landing gear, and how much force the landing gear can take when it hits the ground, okay? The impact. So you design the landing gear, and then you build everything up, the structure up from that, because it has to absorb that landing force. The rest of the structure has to be able to absorb that and dissipate it through the rest of the structure. So you design the landing gear, you have some ballpark of what weight you want for the overall aircraft weight, and then you design the landing gear, and then you build all the structures out from there, the wings, the fuselage, and everything. Fuselage is really just hanging on the wings. In fact, the 747, supposedly the fuselage is held onto the wings with 4 bolts. Very high strength, nickel alloy, super alloy bolts in this kind of strength range, which are not susceptible to hydrogen embrittlement, okay, as far as that goes. So this shows you.
So what, so what, we've been talking the whole time that high strength steels are very susceptible, so why are they, oh, they're not steels there.
These are steels, okay? But the types of steels you guys are gonna use, HY100s down here. Because you gotta worry about, it's gotta be weldable, and you gotta let it corrode some, or allow for the fact that it might corrode. Like, they forgot to put the zincs on the hull, which I thought was, ooh, that's sort of a no-no. And I thought it was interesting, but putting that in the Coast Guard, and you were corroding the boats next, you had to scrap a couple of 23-foot, boats.
You guys have active systems, right?
Yeah.
Yeah, so it's not zinc, it's a potentially equipment.
No, it's a impressed current, which is what the Navy uses. But anyway, in any case, titanium alloys, yeah, they can get to 200 KSI, but in fact for marine alloys, 6.4 is the workhorse alloy in titanium, we'll get to that later. But the Navy has a Thai 100 they developed back in the 60s, but again, it's 100 KSI, but it's a lot lighter, so it gives them greater depth capability for submersibles. You get to the aluminum alloys, and it turns out, I didn't bring it in, I guess I should have, maybe I will tomorrow. The highest strength aluminum alloys are found in baseball bats, aluminum baseball bats. We can talk about why, but up to 100 KSI, or just over 100 KSI, but typical alloys are up in the 80 to 90 for aircraft wings and things like that. 2014 is an aluminum copper alloy, it's been around for since the 1920s. In fact, the Wright brothers engine block for their engine in their flight, which goes back over 100 years, was a aluminum copper alloy. 6061 is the workhorse, about 50 KSI strength. Magnesium alloys, not a lot of them, we'll talk about why. Magnesium has 2 Achilles heels. It has one wonderful property, and that's that it's lightweight. But the 2 Achilles heels, it can't be welded, and it is very corrosion prone. Very corrosion prone. Like, don't look at it, it'll corrode. Okay? To give you an idea of some of these densities, here is a piece of zinc, which is just about 10% less than the density of steel. So you think of the zinc as roughly steel, there's magnesium. You can tell, you can feel the density. Here's aluminum, I don't have it in 1-inch rod. Here's a piece of titanium, okay, but comparable size pieces, and you can feel the heft of each one of those. If you now divide by the density of each one of these, you find titanium's got the highest strength, and all the alloys, all the metals are about the same when corrected for density. Why do we correct for density? Well, if something doesn't move, we don't care about density. You just put it on the ground and the earth doesn't move, and it doesn't move, and there's no problem. But if anything moves, you want it to be lightweight. And the faster it moves, the more you value lightweight. In my material selection lecture, I go through this in some detail. But in any case, we want lightweight alloys. Everybody wants lightweight things. And that's why they look at cells and foams and not silicon gel, but aerogels. And they get all excited because it's so light. Has no mechanical properties, but it's light. But that's sort of what we trade off, is some of these properties. And now you don't see this yet. The aluminum alloys, let's start the aluminum alloys. There are a whole series of aluminum alloys, and the aluminum alloys go by a 4-digit number, just like the American Iron Steel Institute 1018 steel. Okay, there's not a 1018 aluminum, but there's 1,000 series of aluminum, 2,000 series, 3,000, 4,000, 5, 6, 7, and even an 8,000. This book didn't go out that far. But the 1,000 is not heat treatable, it's basically nearly pure aluminum. Example is 1,100 aluminum, it's 99% aluminum. And the rest is just impurities. There are heat treatable alloys of the 2000 series, aluminum copper alloys. Virtually all the aluminum alloying elements like to form a phase diagram, which we're going to see over and over here as we talk about aluminum. That is looks like this. This is temperature. This is percent, I'll call it copper right now, increasing. This is 100% aluminum, and this is like about 4.5% copper, if I remember correctly. Okay. So 660 centigrade is the melting point here, about 540 or so here, 120 degrees centigrade temperature differential. Something that only melts at 660. So aluminum doesn't have really good high temperature properties. In fact, we're going to see that some of them, the heat treatable alloys, are not very good at all at temperatures above even 200 degrees Fahrenheit. Okay, boiling water can wipe them out. So these are heat treatable alloys, and this essentially, 2219 is a modern alloy. That's what they used to build the space shuttle main tank out of. Now they use it up. They lightweighted it. Now they don't build it at all. But 2219 was basically aluminum, near 4.5% copper alloy that was more weldable than some of the others. The Wright brothers, if you tried to weld with a gas tungsten arc, now that you know what that is after yesterday, on the Wright brothers crankcase or cylinder housing for their piston engine, you would crack it. I mean, you could melt it, and you'd have nice cracks. If you pull very hard on it, you just pull that little melted metal right out of there. And you can dip it. Okay? That's all the cracks underneath. Yes? Mike, there's a question? Same type of problem as you have on the Monels and things. You get cracking, liquation, melting in the heat affected zone in the copper rich areas. The non-heat treatable 3000 series, here's your beer can stock. Okay, the largest used most widely used in tonnage alloys. At one time, 40% of all the aluminum in the world went into beer cans. Things like that. Okay, it's a major part of the aluminum industry. Okay, whole billion-dollar plants, and that's all they do is turn out sheet metal to go to the beverage manufacturers, like Coca-Cola or Anheuser-Busch. Not heat treatable, it's got like 1 or 2% manganese in it. It's higher strength than this, but it's mostly there for formability. The heat treatable, not heat treatable 4000 series have silicon in them. Basically, it's welding wire. The most common welding wires are pure aluminum or 4340. 4340 can weld most of the other non-heat treatable aluminum alloys. 5000 series, the Navy uses these for building hulls and has for 50 years. They're basically aluminum magnesium alloys. There are two big uses of magnesium in the world. The biggest use is alloying with aluminum. Okay? And it's like the biggest use of manganese in the world is alloying with steel. Okay? But in the case of manganese, 90% of the manganese in the world goes into steel. In the case of magnesium, I think it's only about 50% of all the magnesium. About 30 or 40% of all the magnesium goes into sacrificial anodes for corrosion in things like hot water tanks and things like that. So it's just a sacrificial anode. Because its best property of all is it corrodes really well, okay? And in fact, the naval Port Quanumi is where a bunch of the divers in the Navy do things, and they have a little test lab, research lab. And a number of years ago, they developed magnesium carbon alloys. They take carbon powders and they take magnesium powders and they press them together. And you could stick this in seawater, and it would, actually, you could try to polish it in the laboratory, and if you used a water-based polishing slurry, it would corrode faster than you could polish it, okay? So they had to use oil-based polishing, fluids. But if you stick it in seawater, one of the things that they found a use for was salvage. You put it in a little plastic bag, the diver takes it down beneath the surface, he gets a big plastic tarp that he puts over and it connects it to whatever he wants. He puts his little plastic coated piece of magnesium carbon alloy in underneath that tarp, breaks it, seawater comes in, and he generates a hydrogen bubble that floats the thing to the surface. Okay, that's how fast it corrodes. So you can generate your own hydrogen underwater. Okay, so it was pretty cool. You don't have to carry around big tanks of gas that are lighter than water. You can carry on around a little thing, and the water will produce your own gas, hydrogen. So just don't apply the match when it gets to the surface. Okay. Very cool. Anyway, the other thing they did with it, it corrodes so fast that in cold environments, they can strap it to the diver's belt, and he can take his knife and he can puncture the bag, and it will corrode and generate enough heat to keep him warm. So, okay. But those are two applications, just to give you an idea of how fast magnesium will corrode. Okay, it really corrodes great. Okay, that's why we don't use it much. Okay, but the Department of Energy has been spending tens, if not hundreds of millions of dollars every year for the last 50 years because, if we can use magnesium in automobiles, we can take out 1,000 pounds out of every automobile. And you know what? It'll be great for sales. You'll be replacing those cars every 6 months. Okay. And in fact, they do use magnesium under the dashboard where you can't see the corrosion. Okay? And where what's protected from the elements, okay, it's the passenger compartment, right? So under the dashboard, some of the dashboard substructure will be a cast magnesium panel, okay?
They use it in aircraft too, right?
They use it in helicopters and other aircraft because, helicopters get 2 hours of maintenance for every hour of flight. And if you're going to check things that often, on your maintenance, you can use it for aerospace when you need lightweight. It's great material, okay? Just has a few maintenance issues, okay?
Aren't the brakes on aircraft usually magnesium or rims?
The brakes on aircraft, big aircraft, are actually carbon-carbon composite, okay? Very expensive, and in fact, they're very expensive. It's possible that they might use some magnesium in some of the calipers and stuff, the structure that holds the brake pads, but the brake pads can get so hot when you're trying to stop 450 tons rolling down the highway at 100 miles an hour when it lands, okay? You need to dissipate a lot of energy. In fact, I watched a program years ago on the certification process of the Boeing 777. And they basically had to land the aircraft and stop it in such and such a distance, and then the brakes could catch fire, but they had to have at least 3 minutes before the fire crew could put it out. Because, in a real world situation, the fire department's not standing right there where the plane comes to a rest at the end of the runway. So they had to give them 3 minutes to get there. But you had to basically pass some test where you don't destroy the rest of the engine or have hydraulic leaks and things like that for 3 minutes. You can have a big flaming fire as your carbon-carbon composite brakes start to go on, burn. You gotta remember, carbon-carbon composites are what we use for cruise missile engines and things like that. Take high temperatures but they don't last very long. But bikes don't last very long either, okay? Anybody know how they commercially, they handle brake wear in the commercial airlines? It's per landing. The United or American or whatever, they don't own the brakes. Honeywell, who makes the brakes, leases the brakes to the airline, and if they wear out quickly, Honeywell they got a contract, they have to have brakes. You know, if you're the mechanic working for United or American and you look at it and needs to replace the brakes, doesn't cost you anything except the time and the labor to replace the brakes, but Honeywell pays for all brakes. So Honeywell has an incentive to develop brakes that will have a long lifetime. And the aircraft, or the airlines, know exactly how much they're spending on brakes for every landing, because they're paying by the landing, okay? They do the same thing now with engines. Either Pratt & Whitney or General Electric, if they want to carry the investment, or it could be a brokerage firm or something that basically leases the engine to the airline, and the airline pays so much. They cost power by the hour, okay? They pay so much for every hour the engine operates. And so the owner of the engine has every incentive to make engines last for a long time and not have to go back for maintenance overhauls, because they're getting the profit out of a long-lasting engine. They have a lot of maintenance problems with their engines. Again, the mechanic has no incentive to not replace the engine if he sees something wrong. Doesn't cost anything. New engine, hey, you know, the brokerage company or Pratt & Whitney, they got them in their tubs. You know, they come in these circular shipping casks. They got them there, and just the labor and the time to bolt in and, you know, take out the old engine, bolt the new one in. But that's the way they're doing it. And even people are getting to the point where the commercial airlines, they don't even want to own the aircraft, okay? I haven't quite gotten to aircraft by the hour that I know of, but they're kind of heading in that direction, okay? They start out with brakes, and then the engines, and it does provide a lot of right incentives for the mechanics, okay? Replace it if you need it. Now, there is a balance in that the airline still has to pay for the labor to replace it, but the cost of the parts are paid for by someone else who's getting a fee for every landing or every hour of operation. We have the 5000 series are not heat treatable. We can get full 100% strength of the weld, 100% joint efficiency. Workhorse alloy is 50-52, the Navy uses 54-54, or used to. They've come up with a couple of new ones now. Heat treatable magnesium silicone alloys, where you have to heat the aluminum up, quench it in water, and then bring it up and temper it. High strength, you can get double the strength of the 6000 as the 5000, but when you weld it, you can weld 60-61, you may only get 50% or 60% joint efficiency. You cannot get 100% joint efficiency in heat treatable alloys. They have twice the strength, but once you weld it, everything becomes a casting again, and castings are not heat treated. I mean, you could weld it and then reheat treat the weldment, okay? And you can get the strength up there, but that gets really expensive, and usually the weldments are complex shape, and they're going to distort or everything else that you don't necessarily want. There's the 7000 alloys. These are the highest strength, and these are things like the wings on the aircraft and stuff. And then off to the end, where we don't have anything on this one, we have the 8000 series, which is a catch-all, and it now includes aluminum lithium alloys, which have, it says, in this little ranking, other elements is 8000 series, and 9000 is still in use, okay? So far as that goes. But those are the standard designation alloys for aluminum.
Professor,
Yep.
the other day you showed us that stainless steel pot that was cracking because they punched it out. You said the bottom was aluminum.
Yeah.
And I was looking at that. None of that really. I guess why do they use aluminum at the base there?
Because it has good thermal conductivity.
I thought you were
Steel is lousy.
I thought you were saying like even boiling water sometimes could damage it, you were saying.
If it's aluminum alloy that has copper or magnesium or other things in it, that thing on the bottom, pure aluminum.
Okay.
Pure aluminum has excellent water corrosion resistance. The right aluminum alloys have excellent water corrosion resistance. We build sewage treatment plants out of aluminum. They don't rust, okay? If you pick the right alloys that don't have pitting or stress corrosion cracking problems, and there are plenty of aluminum alloys that don't have that, they tend to be lower strength. But you go down here to Deer Island treatment facility where what they do the cleanup of Boston Harbor water, it's all aluminum, okay? All welded aluminum. Lower strength, you're not looking for, it's just piping. You're just carrying water. Kind of dirty water, but you know, it's just water. So aluminum actually has excellent corrosion resistance. I mean, you know that because the aluminum frying pans, okay? But for instance, aluminum foil. A regular fire may be just above the melting temperature of aluminum, but you don't generally melt the aluminum cooking surfaces. Why? They're steam cooled. Usually you're cooking something that has water in it. In fact, hey, you've been a Boy Scout, you ever had a foil dinner? You wrap it in aluminum foil. If you put a steel bolt in there and put it in the fire, you'll probably melt your aluminum because there's no steam to cool the aluminum foil. Okay? But you can melt a pure aluminum foil with a good hot fire. Okay? But you don't usually do it because just a little bit of moisture, and it comes with what you're cooking usually. Okay? That's a little physics of heat transfer that people don't usually tell you. Okay, so if we, well, this is just giving you some aluminum. Actually, why don't we take a break if we're going to take, you want to take a, you need a 10-minute break or you want to just go to 9:30? Why don't you take a